All right, so in this video, I want to talk about section 11.2, and this is going to be the section all about series. But before we get to the new stuff, let me remind you of what we did in 11.1. So in 11.1, we talked about sequences. Sequences are just ordered lists of numbers. So things like a sub n is n goes from 0 to infinity or from 1 to infinity or whatever. And that's a sequence, just an ordered list of numbers. That's the end of the story. A series is going to be the sum of the values in a sequence. So the sum of the values in a sequence. Okay, and so, for example, we could talk about the sequence 1 over 2 to the n as n goes from 1 to infinity. That's the sequence 1/2, 1/4, 1/8, 1/16, 1 over 32, and so on. Okay, and we could go as far as we want. And that's a sequence. The series is the sum of the values. So if we add up the values, 1 over 2 to the n as n goes from 1 to infinity, that's the series. And so we have a few questions that we need to answer here. Does this series even make sense to begin with? So is this something that we can actually talk about and then we get some number like 5? Or is adding infinitely many numbers just going to inevitably force all these values to go to infinity? Is there a way to decide what the sum is going to be? So these are some of the issues that we're going to talk about in this section. Now, 1 over 2 to the n happens to have a very nice geometric picture. And so what I'm going to do is I'm going to draw a square. At least I'm going to try to draw a square. My iPad helping me out at least a little bit here. And what I want to do with this square, let me fill it in just a little bit here. What I want to do with this square is I want to color in a half of it, and then a fourth of it, and then an eighth of it, and see what happens. So if I were to color in, say, the bottom half, say that that's approximately half, and then I were to color that in, okay, I could color this in nicely if I spent more time, but you get it. I'm shading half of it. And then on top of that, I'm going to shade a fourth. Okay, so that's shading in a fourth. And then on top of that, I shade an eighth. Okay, so there we're shading in an eighth and then a 16th. And I keep cutting this unshaded region in half and filling it in. What happens if I do this all the way to infinity? So do this until you get sick of it. Right? We keep doing this and doing this and doing this. There's still this piece up here that's not filled in, but this is getting more and more filled in. And the more you zoom in, right, the more obvious that you can just keep cutting this in half and filling it in, and you can do this for forever. You'll never exactly fill up the entire square, but you can get as close to having this filled up as you want. Okay, so if you want to make sure that at least like 90% of it's filled in, you just have to fill in enough pieces here until you get to at least 90%. Okay, which I think we're already there. If you wanted to make sure that this is like 99.999% filled in, you just have to do enough terms until you get there. And so eventually we're going to fill up the entire square. That's going to be 100% of it. So I know that eventually we'll get past 99.9% or whatever number I said before. So that's this geometric series. And this, that's this series. It is called the geometric series, but for reasons later that we'll talk about. It's just that there's a nice geometric picture that goes with it. So this series with this nice geometric intuition, what we seem to have just shown is that the series is 1. Okay, so the series adds up to 1, and that turns out to be true, and we will justify that. The way that we justify it is to introduce a second sequence given the sequence 1 over 2 to the n. And so given the sequence 1 over 2 to the n, okay, as n goes from 1 to infinity, I want to define the sequence of partial sums. And so we denote this as S capital N. So S of capital N is capital N goes from 1 to infinity. Okay, and so here what we mean by S of capital N is this is going to be the sum of all the values, not to infinity, but to capital N, as little n goes from 1 to capital N. So for example, the sequence the value S sub 1 is just going to be the sum of 1 over 2 to the n as n is equal to 1. So it's 1/2. It's really not too much to do there. S2 is going to be the sum as little n goes from 1 to 2. So it's going to be 1/2 plus 1/4. And again, I better just write this just to make sure we're all on the same page here. This is the sum 1 over 2 to the n as little n goes from 1 to 1. S2 is the sum as little n goes from 1 to 2. S3 is going to be the sum as little n goes from 1 to 3. So that's 1/2 plus 1/4 plus 1/8. Okay, so that turns out to be 7/8. The previous value being 3/4. I forgot to say that. And then let's just do one more. So S sub 4 is going to be the sum as little n goes from 1 to 4. So this is 1 over 2 to the n. So that's 1 over 2 to the first plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the fourth. So that's 1/2 plus 1/4 plus 1/8 plus 1 over 16. And that happens to be 7. So we know that the first 3 values add up to give us 7/8. And then we're going to add 1/16 to that. So 7/8 is 14 over 16 plus 1 over 16 is 15 over 16. And so apparently the pattern is that S of capital N being the sum as little n goes from 1 to capital N, okay, is going to be 2 to the capital N minus 1 over 2 to the capital N. Or if you want to write this as 2 to the n over 2 to the n minus 1 over 2 to the n, this is just 1 minus 1 over 2 to the n. So that's the nth partial sum. Now, what do the partial sums have to do with the infinite sum or the series? Well, it turns out that, I'm out of room here. It turns out that the infinite series, the right way to define this infinite series, is the same as the way that we defined improper integrals. This is going to be the limit as capital N goes to infinity of the sequence of partial sums. So in other words, the sum as little n goes from 1 to capital N of 1 over 2 to the n. And we just said that apparently there's a formula here that this is 1 minus 1 over 2 to the capital N. And that tells you that that limit really is 1. And this also tells you, this kind of explains that geometric behavior with that square a little bit nicer. To say that the limit is equal to 1 means that eventually, if you add more and more and more and more terms, the amount of this square that you fill in is approaching 1. And we're going to get arbitrarily close to 1. This gets as filled in as you like. Even if you stop after a finite time, you never quite get there. You can get as close as you want to filling in the whole square. Okay. And so we use the same language because this is so similar to improper integrals. We use the same language. So we say that this series of 1 over 2 to the n converges to 1 because the limit of partial sequences converges to 1. Okay, so this series converges to 1. And again, I like to think about it like this. I like to think about this infinite series as the limit as capital N goes to infinity of this sum over a finite number of terms, just as capital N is going to infinity. Okay, and so this is, in our case, this series converges to 1. So in general, what's going to happen, you're going to start with a sequence. So this is kind of the original sequence A sub n. You're going to look at the sequence of partial sums. So you have the sequence of partial sums, which we denote usually S sub capital N, where S sub capital N is usually the sum of all the values in the sequence up to capital N. And then you have the infinite series, which is the sum of all the values in the original sequence, okay, from 1 to infinity, which we think of as the limit of the sequence of partial sums. Again, very much like an improper integral. Okay, and that's kind of the setup. A few other just bits of terminology, and then I'll call this, we'll be done with this video. I want to break up this section into lots of kind of small, palatable pieces so that you can kind of go back and review if you need to. But just a little bit of terminology. We say that this series converges if the limit as capital N goes to infinity of the sums, little n goes from 1 to infinity. Keep doing that. If the sum is little n goes from 1 to capital N, converges. And then if the limit as capital N goes to infinity, so sum from little n to any little n going from 1 to capital N, if this diverges, then we say that the original series diverges. So we're going to use the same language. And again, we can talk about diverges to infinity, or just plain diverges. Maybe we're talking about the limit of some quantity where the numbers keep oscillating. Maybe we have some positive and negative terms and they cancel, but they never settle on a particular value. So we're going to use the same terminology of converging and diverging, just like we did for sequences, just like we did for improper integrals. Okay, so that's really the starting point for 11.2.